MySpace, launched in 2003, used to be the largest social networking site in the world. In 2005, a 20-year-old named Samy unleashed on MySpace the fastest spreading self-replicating worm of all time, which infected over 1 million accounts in less than 24 hours. If you were a MySpace user and you visited the profile of an infected user, your profile would immediately become infected as well. You would make Samy your friend, your profile would say that Samy was your hero, and anyone visiting your profile would become infected too. We have a seed lab that recreates a social networking website where various users have profiles and friends. Can you repeat Samy's exploit and write a self-replicating worm that will virally spread from your profile to those of everyone else? Welcome to Frank Stajano Explains. My name is Frank Stajano and I am a professor of security and privacy at the University of Cambridge. This is a lecture in the cybersecurity course I teach to second-year undergraduates. All other lectures are in the playlist up there. Today's topic is cross-site scripting, often abbreviated as XSS, which is the vulnerability that Samy exploited for his MySpace worm. Today's lecture is complemented by the seed lab on cross-site scripting, of which I want you to do at least tasks 1 to 6. It's even better if you do task 7 as well, but I'll leave that as optional. If you are my student at Cambridge and have access to the course handout that is currently reserved just for you, notice that since this is the first year I run the course in this format, I keep improving it every few days and as I record new lectures, and you will get the latest version if you access the electronic copy from the link on the course webpage. In particular, regarding today's lecture, I have added some hints on small gotchas that you might encounter when getting the seed lab to work. The usual warning applies. Stay legal. By all means, become proficient at these attack techniques, but do not deploy them on live systems. This guy thought he was just having a laugh, becoming popular and increasing his chances of getting laid. Always helps to have a good motivation, of course. But he was then raided by the United States Secret Service and Electronic Crimes Task Force, had to plead guilty to a felony charge of computer hacking, served 3 years on probation without internet access, and narrowly escaped a prison sentence. Just be sensible, all right? As a competent cyber defender, you can be a well-paid hero without having to be a Cross-site scripting is another kind of impersonation attack in which the attacker causes a malicious action to be executed while the victim's cookies are active. The attacker Albert tricks the victim Victoria into executing some malicious code, typically JavaScript, in her browser. Since the malicious code executes in Victoria's browser with Victoria's credentials, it can do most of the things that Victoria has authority to do. Some people confuse cross-site request forgery, which we discussed in a previous video, and cross-site scripting. They are somewhat similar. Both involve some modest amount of social engineering, which is tricking the victim to visit some URL, and both exploit the victim's authentication cookies for impersonation, requiring the victim to be logged in. But CSRF only lets the attacker run, as the victim, one of the possible transactions that are already offered by the website. Submitting a form, basically. The website must be expecting responses to that particular form. Whereas cross-site scripting lets the attacker run arbitrary code as the victim in the victim's web browser, which gives the attacker greater freedom. The attacker can do her own scripting rather than merely a request forgery. One more first question, the basic assumptions here. If people are willing to turn on JavaScript, they are already willing to accept that arbitrary websites can execute arbitrary code in the browser, right? So what do they complain about if some of that code is malicious? Shouldn't they just disable JavaScript? Well, in today's world, that battle has largely been lost. Even though some of us refused for many years to run with JavaScript enabled, nowadays some 97% of websites rely on JavaScript, and basically nothing works properly if you leave it off. So what mitigations are in place? Well, there is some amount of sandboxing with the intention that the JavaScript you get from one web page can only access objects in another web page if both pages have the same origin, the so-called same origin policy. And of course, the JavaScript served to your browser in a page from Wallbank can do anything it wants to your Wallbank account, but that's not an issue because code under the control of Wallbank could do anything it wanted to your Wallbank account anyway by doing it at the server side, even if JavaScript didn't exist. The point of same origin policy is that the code from Wallbank should be allowed to do whatever it wants to Wallbank objects, but Not for that should it be allowed to mess around with any of the pages you have open concurrently in other browser tabs. For example, there's no reason why it should be allowed to read the messages in your webmail. The core idea of the cross-site scripting attack is to violate the assumption that the JavaScript you get from Wallbank was written by Wallbank, and then to do devious things to your Wallbank account while logged in as you at Wallbank. Attacker Albert arranges for victim Victoria to receive malicious JavaScript written by him, but which is served to her by Wallbank, and which Victoria therefore trusts while she is on Wallbank's website. In a sense, this is the reverse of cross-site request forgery. There, Albert fooled the server Wallbank into believing that the fake request originated from the authenticated client Victoria. In cross-site scripting instead, Albert fools the client Victoria into believing that the fake code originated from the server where she has an account, which is Wallbank. There are two main types of cross-site scripting attack: reflected and stored. Let's first talk about reflected. What Albert may do is to exploit situations where Wallbank is serving Victoria a page that isn't merely static, but which contains content that depends on user input in some way or other. And then Albert needs to manipulate the user input so that the page generated by Wallbank and served to Victoria contains the malicious JavaScript payload that Albert wants to execute within Victoria's browser. We witness another instance of a problem that frequently recurs in this course: malicious code disguised as data. Normally, when Wallbank serves a page with content that is a function of user input, the expectation is that the user input that is going to be reflected in the Wallbank generated page is just data, not executable content. But many websites don't check, or don't check carefully enough, and even when they check it's really hard to be absolutely sure, and as a result, some executable content may slip through. Let's first assume that Wallbank does not perform any sanitization checks, and let's see what Albert can do to cause his executable JavaScript to be served to Victoria when she visits the Wallbank site. A non-persistent cross-site scripting attack exploits the case where some page of the website has a form accepting user input and where the responses to that form reproduces that input. Imagine that Wallbank embeds a search engine in a corner of its pages. You type foreign exchange in the search box, and Wallbank returns a page saying, "Here are some pages that I found that relate to foreign exchange," followed of course by the link to those pages. The important point here is that Wallbank repeated your text verbatim back to you, foreign exchange. Now, what if your text contains some HTML tags, such as foreign boldface exchange, the angle bracket B to make the second word boldface? Would the result page again reproduce your text byte for byte, tags included, causing the tags to be interpreted by your browser and making that second word bold? Or would it somehow quote your text before reproducing it on its output page, transforming foreign angle bracket B exchange angle bracket /B into something where the angle brackets get quoted with ampersand less than and so on, causing the angle brackets to be displayed rather than be parsed as tag delimiters? Whether it would do one or the other is a matter of policy and implementation, but unless the website is extremely strict with its quoting, then it might possibly also let through an HTML tag such as angle brackets script, which, when interpreted by the browser at the time of rendering the response page, would cause a script to be evaluated as code and therefore executed in the viewer's browser. Albert's attack therefore consists of crafting an input to that form that will cause the desired malicious script to be executed when the response page is rendered, and then to arrange for Victoria to submit that input to the form. This in turn could be done by preparing a GET or a POST URL that did the submission to the form and then tricking Victoria into clicking on it, using similar social engineering techniques to the ones that we mentioned in the context of the cross-site request forgery. In a persistent cross-site scripting attack instead, Albert covertly stores his malicious executable at Wallbank server-side. He exploits a situation whereby the website allows users to post content that will be seen by other users, such as messages on a bulletin board, or discussion forum, or comments on a blog post, or profile page on a social media site, and so on. Provided that HTML tags are not completely sanitized, this lets Albert store his executable payload in the Wallbank backend, on a page that Wallbank will happily serve to other users. If Victoria or any other Wallbank user is logged into her Wallbank account while she views that page, Albert's malicious code, blessed by the legitimacy of having been served by Wallbank, will execute in her browser with her Wallbank cookies active, and will therefore be able to do most of what she could do herself in that context. The privilege escalation in this web context is no longer gaining root access, as it was in the attacks on setuid programs that we saw in an earlier video, but rather getting the privileges of the victim. Once the attacker can run arbitrary JavaScript code in the victim's browser while the victim is logged in, then he can edit the victim's profile, he can change or deface any pages that the victim has write access to, he can post messages purporting to be from the victim, he can take any actions that the victim is allowed to take, transfer funds, buy items, whatever action is allowed on that website for the legitimate user. For any piece of information that is available on the victim's pages, her account balance, her credit card number, even her login cookie, then it is trivial for the attacker to display it on screen by popping up an alert box, which is done trivially with just one line of JavaScript like that. The trouble is that for the attacker that the JavaScript is executing in the victim's browser, so it's on the victim's screen that this alert box is displayed, which does the attacker no good. How can the attacker exfiltrate any of the information that his malicious JavaScript can access and manipulate? This is one of the initial tasks you will have to perform in the seed lab. An ingenious idea is to use input as output. There are no restrictions on JavaScript requesting input from other websites, for example by adding HTML image tags to the document that would load pictures into the page from other sites. But it takes a bit of lateral thinking to realize that this input facility in fact is also an output facility, because it is also sending something in the opposite direction, in particular the name of the picture file that is being requested. So from the malicious JavaScript now running in Victoria's browser, Albert simply requests non-existing images from his own server, his own attacker server somewhere on the network, where the names of the images encode information that he wants to exfiltrate, for example Victoria's login cookies. He then checks the logs of his web server to see what requests came in. Another one of the tasks that you will be doing in your seed lab, described in detail in your computer and internet security textbook, replicates the Samy Camcar worm I mentioned in the opening of this video. The payload of the worm was simply to add Samy as a friend and to add a declaration to that effect in the victim's profile. But most of all, Samy is my hero. And the worm was self-replicating, so any user viewing an infected profile would execute that same payload and in turn become infected. When it came out, the Samy worm was the fastest spreading piece of malware ever seen. Within less than a day from its release, it had infected over 1 million user profiles. There are several instructive write-ups about this incident on the net, some more narrative and others more geeky. A short one with a wealth of technical details is the one on Camcar's own website, which also contains the full code of the worm. To mount a persistent cross-site scripting attack, Albert must first of all find a vulnerable page at Wallbank, one that lets him store his HTML input without filtering out his JavaScript. Once he has that foothold, to craft a payload that does anything interesting as Victoria, he will generally want to submit a form as Victoria. As we saw with the cross-site request forgery, the case of GET is easily handled because both the destination and the parameters are encoded in the URL. The case of POST is somewhat more elaborate, but it is not a problem since Albert is in a position to write his own JavaScript. So he builds an XML HTTP request object, populates it appropriately, including inserting the parameters in the content of the request, and then invokes the send method of this object. The parameters may include the security token that Wallbank requires as protection against cross-site request forgery, as we said in the CSRF video that is linked from one of the cards that you may get by expanding the little circle that's in the corner of your screen. Albert has no trouble including that token because it is available as a variable to the JavaScript code that is running on that wallbank page. You will learn how to do this in the Seed Lab, which provides some boilerplate JavaScript code with blanks for you to fill in once you work out what the actual request ought to be. And here's a fragment of the JavaScript boilerplate that submits a post form. You have to figure out, among other things, the content and the send URL in lines 5 and 6 respectively. And how do you work out the correct parameters? Well, you can do that by observing a genuine transaction as it goes through, for example, using Wireshark or using Firefox built-in Web Developer Tools network. You'll be doing that as well in the Seed Lab. As you do that, you will pick up that there are many ways of encoding the content of the request, and that while not all of them are appropriate for all types of content, many things can be encoded in more than one way. Here's part of what Wireshark shows when Samy the attacker changes his own profile to something innocuous on his way to building his more malicious payload. Notice here that the transaction you observe might encode the form data in a relatively complicated way, such as the content type multipart form data that we see here in the Wireshark capture. But you are free to submit your own response using a different encoding, such as the easier to write content type application XWWW form URL encoded, which is used in the boilerplate that I showed earlier, which is in fact similar to the style of the get parameters with the ampersand and name equal value pairs. So look these things up on the web as you need them. You're not expected to know everything already, but you are expected to acquire the skill to solve practical problems. What about countermeasures? As in other contexts involving data as code attacks, there are two broad approaches to preventing cross-site scripting. The first one is sanitization, either to filter out the code from the user input and throw it away, or alternatively to filter out the meta characters and the tags through which the attacker input is parsed as code, leaving the JavaScript source in the input but just as text. Sanitization can be a useful first line of defense, and it's certainly better than nothing, but it is generally difficult for it to cover all cases. For proof of this, check what Kamkar himself had to say about how he bypassed the numerous sanitizations that were present on MySpace at the time. Very instructive and sobering for someone who thinks that blacklisting dangerous inputs will keep the hackers out. So he said, MySpace blocks a lot of tags. In fact, they only seem to allow angle bracket A, angle bracket images, and divs, and maybe a few others, embeds I think. They wouldn't allow scripts, bodies, on clicks, on anythings, hrefs with JavaScript, etc. However, some browsers, Internet Explorer, some version of Safari, others, allow JavaScript within CSS tags. We needed JavaScript to get any of this to even work. So for example, div style background URL, JavaScript, and then the JavaScript code alert1. Gives an example of a place where he could insert some JavaScript because it was inside a CSS tag. A second point, we couldn't use quotes within the div because we had already used up single quotes and double quotes already. Just check the fragment above. This made coding JavaScript very difficult. In order to get around it, we used an expression to store JavaScript and then executed it by name. Example, div id my code, expression equals alert ha, alert ha is the JavaScript, style background URL, so again within a CSS tag, JavaScript eval document all my code exp. So he retrieves from the document object model the expression that he had previously stored, which is the JavaScript. Sweet! Now we can do JavaScript with single quotes. However, MySpace strips out the word JavaScript from anywhere. To get around this, some browsers will actually interpret Java new line script as JavaScript. Example, div id my code expression alert ha, style background URL Java new line script eval document all my code expression. Okay, well, while we do have single quotes working, we sometimes need double quotes. We just escape quotes, for example, foo \quote bar. MySpace got me. They strip out all escaped quotes, whether single or double. However, we can just convert decimal to ASCII in JavaScript to actually produce the quotes. For example, div id my code, exp alert, double quote, plus string from character code 34, which is the ASCII for the double quote, style equals background URL, JavaScript eval, document all my code expression. In order to post the code to the user profile who is viewing it, we need to actually get the source of the page. We can use document body inner HTML in order to get the page source, which includes, in only one spot, the ID of the user viewing the page. MySpace gets me again and strips out the word inner HTML anywhere. To avoid this, we use an eval to evaluate two strings and put them together to form inner HTML. Example, alert eval document body inner plus the other string HTML. And it goes on, and it goes on, and it's very interesting. I suggest going through in detail after you have completed the seed lab yourself, so you can admire all the interesting things he did. Anyway, this business with sanitization is not just MySpace's problem. It has repeatedly proved very hard to anticipate all the possible ways through which attackers may slip under the radar of this kind of checks. See, for example, having split a keyword over two strings. If adopting input sanitization, it is a good idea not to roll one's own filter, but to rely on a well-tested library developed and maintained by the developers of the web framework or language in use. But there is an alternative to sanitization that is somewhat more principled. The root cause of the cross-site scripting vulnerability is that the browser does not know the provenance of the JavaScript code it is being asked to execute. Was it written by Wallbank or by Albert? If we could give Victoria's browser that piece of information, we could also instruct it to execute only the code from Wallbank. As we have seen, in cross-site scripting, Albert's code is served from Wallbank's server. Indeed, it is embedded in a page served by Wallbank. So it seems as if that battle is already lost. But what if HTML code, which is not executable, were not allowed to embed JavaScript code directly, and were instead only allowed to embed URL references to JavaScript source code files to be downloaded? Then Victoria's browser would be in a position to tell where that JavaScript came from, and it would be able to reject any JavaScript not coming from Wallbank. Whether it did reject it or not would be decided by a server-specific content security policy, CSP, specified by the website in the HTTP response headers of the pages it served. As usual, from the security viewpoint of preventing cross-site scripting, it would appear preferable to exclude embedded JavaScript altogether and force all JavaScript to be imported from URLs, so the provenance was clear. But there's the usual trade-off between security on one side and developer convenience and backwards compatibility on the other side. The optional task 7 of this seed lab gives you the opportunity to experiment with content security policy in various forms to block cross-site scripting attacks. With cross-site scripting and cross-site request forgery, we have been dealing with web vulnerability, and we have been working at the HTTP level. HTTP is implemented on top of TCP, and there are specific vulnerabilities in that level as well. In our next video, we'll be looking at 3 of them: SYN flooding, TCP reset, and TCP session hijacking. Any experience you gain with Wireshark in today's seed lab will come in useful when you get to this other video. If you enjoy these videos I'm making for you, then please reward them with a like. It helps tremendously. And subscribe to be notified as soon as new ones come out. Thank you very much for watching. Have fun recreating the Samy worm, and I'll see you in the next video.